All right, so we got our 5.6 notes here. Continuing with this idea of finding probability and then independence as well. So building on what we started in 5.3, 5.4, continued in 5.5. And so now we're looking at this idea of snow days, which we're not familiar with here, but can understand here in Fresno, maybe make it into a rain day calculator, especially with traffic jam, because all of a sudden here in the Fresno Sanger area, we get a little rainy day like we've had the last couple weeks, and we all forget how to drive. All right, so snow day calculator here. So you see the probability for Monday, Tuesday, Wednesday, Thursday, Friday. All right, so let's find some probabilities here. So first one here, probability of Thursday having a snow day, as you can see, is 0.7. And then the interpretation of that is that there's a 70% chance of snow on Thursday. All right, so remember, that's a really high percent chance, but is not a guaranteed on there. And then Friday, we have a probability of 0.6, which similar, right? 60% chance of snow on Friday. So the real question is are the events Thursday snow day and Friday snow day independent? All right, so I know we did some math in 5.4 to kind of figure that out, but just think about that. Is it more likely on Friday to snow if it snowed on Thursday? And so I would say yes, that is true. So therefore, no, those events are not independent. So Thursday, snow day. Will affect the probability of snow on Friday. All right, which makes sense. For the most part, with rain, as rainstorms come in, if it's going to rain on one day, it's more likely to rain on the next day. And so you have that. And so there's an effect there. And so therefore not independence. So the question here is we're going to find the probability of Thursday snow day and Friday snow day. So and, all right, remember, is multiplication. So we should be able to do 0.7 times 0.6, which would equal 0.42%. Because we're using this probability of event A and event B is equal to probability A times probability of B, but that is not true because we said no, those are not independent. Hey, if they were independent, we could do what we said there, probability of A times probability of B. But since they are not independent, we can't do that. And so what we can do is we need probability of A times the probability of B, which is Friday, but given that A happen, and that makes a difference because they're not independent. So A has an effect on B. So that second one we're going to multiply, which is similar to the one that we were doing over here, right? A times B. But now we have to account for A actually happening. All right, now let's look at our traffic jam calculator for the week. So probability of Monday traffic jam is 0.4. Very similar to snow day. So there's a 40% chance of a traffic jam on Monday. And then Friday is 0.7. And then similar 70% chance of a traffic jam on Friday. Now, are these two events independent? So is a traffic jam happening on Monday, is that going to have any effect on a traffic jam on Friday? And so what I would say is, yes, they are independent, that Monday is not going to affect Friday. Yes, a Monday traffic jam is not likely or doesn't at all affect Friday's traffic. Right? Unless there's construction going on, we would not expect a traffic jam on Monday. Who knows what's going on? There may be something specific. Could be a rare event of an accident, traffic light out, something like that. And generally those will not affect your traffic jams going forward in the week. And so with that, we can now look at 8. So similar to what we did above, right? Because we still have and, which generally means multiplication for us. But since they are independent, the probability of a traffic jam happening on Monday and on Friday, we can just multiply those two probabilities together, giving us the probability of a traffic jam to start the work week and end the work week is going to be 28%. And then probability of traffic jam every day of the week, going to go with, these are independent. Most likely traffic jam on one day is not going to affect the other because most things get cleared up, even if it was an accident. And so traffic jam on Monday, even though it's just the next day of Tuesday, generally not affected, and so therefore all going to be independent. So then we can write all of those probabilities for each day of the week and multiply all of those together, and we get 0.0084 or 0.84%. So probability of having a traffic jam every day of the work week is going to be less than 1%. All right, now, what's the probability of no traffic jams all week? So let's go back and let's just look at Monday. So the probability of a traffic jam on Monday is 0.4. So then what is the probability of not having a traffic jam? Well, there's only two options, right? We can have a traffic jam or we cannot have one. So if having one is 0.4, not a traffic jam, okay, or written with our symbols, traffic jam C, all right, the complement of that is going to be 0.6. And if we apply that across the board, Tuesday would be 0.8, Wednesday would be 0.7, Thursday is 0.5, and Friday is 0.3. So then for no traffic jams, we can then just multiply those individual probabilities from each day together, giving us 5.04%. All right, now think of this. What is the complement of at least one traffic jam this week? All right, so what does at least one traffic jam look like? So we kind of judge this out. At least can look like, hey, a traffic jam on Monday and then nothing the rest of the week. Could be one on Tuesday. Could be one on Monday and one on Thursday. Could be one every day of the week. All right, and we can keep going on. This is going to take a while to list all these out. So that's why we want to try to identify the complement. And so if we think of that in terms of there can be one traffic jam during the week, there can be two of them, there can be 3 traffic jams during the week, there can be 4, and there can be 5, one every day of the week. And the combinations of how those work, right? So Monday, Tuesday for a 2, or Monday, Wednesday, or Tuesday, Friday. It doesn't matter. We're just looking at those are the at least one traffic jam. But you have all of those combinations. Well, instead of trying to write all of those out and figure out those probabilities, there's a simpler way. What is the one option we're missing here? If at least is either 1, 2, 3, 4, or 5 traffic jams during the week, the only other option left is 0. You can also have 0, and that is the complement of at least 1. All right, so complement is no traffic jams. Well, we already found what that probability is. That's this right here. So if I want the probability of at least 1, and this at least is a big phrase here, going to come across this a good amount. And if you pay attention and carry this idea forward, instead of having to do those plus so many more, right? That's just the tip of the iceberg there. You can save yourself a ton of time by understanding this idea of the complement. So we know that 100% of all possibilities has to be in this grouping. Well, the no traffic jams, that 0 is there. So if I subtract that amount, that will then give us the at least amount. So at least one traffic jam will have a probability of occurring 94.96% of the time. All right, so let's formalize that there. So you can go and pause and copy down these notes. And so let's talk about these. So we have the general multiplication rule. All right, one of the things we talked about previously. So this, and notice probability of A happens, then we have to look at that of probability B given that A happen. And so that's conditional probability. Remember, this is how we define conditional probability in 5.4. And so now it happens with multiplication of finding multiple events. And then if events A and B are independent, key phrase, then we can go ahead and just multiply those two things together. And it's often done for multiple events. So multiple events is going to multiply those ideas together. And then the super big one, because it saves you a ton of time, is the probability of at least 1 is going to be 1 minus the probability of none. So to having to find all of the other possibilities, you just have to find, hey, what's the probability of one way? None, because there's only one way none can happen. and then we can subtract that to find the others. All right, so let's look at these two contextual ones here. All right, so the first trimester screen is a test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. Assume that test results for individual women are independent. All right, so key phrase there, independent, will save us a good amount of work. All right, 1. Suppose that two unrelated women who are having normal pregnancies, Devondra and Miranda, are given the first trimester screen. What is the probability that Devondra gets a positive result and Miranda gets a negative result? And so let's think about what those probabilities are and kind of write them out. So we have the probability that Devondra gets a positive, so we'll go D plus, and we're going to multiply probability of Miranda gets a negative result. Well, we know that approximately 5% of normal pregnancies will receive a positive result. So that means Devondra is going to be 0.05. But then a negative, there's only two options again. So if 5% is a positive, well then 95% has to be the negative. And so 0.95 there. And since, again, we know they're independent, we can just multiply those together. Devondra getting a positive has no effect on Miranda. And we end up with 0.475 or 4.8%. And last one, if 100 unrelated women with normal pregnancies are tested with the first trimester screen, was the probability at least, so you see this, okay? At least alarm bells should be going off because you're going to be thinking, hey, I want the probability of at least 1, and that's going to be 1 minus the probability of none. And in this case, we want none positive. And rewriting that conceptually, that's 1 minus the probability of a negative. Well, probability of all negative, I should say, is going to be 1 minus 0.95 for negative. And the second one has to be negative, and the third one has to be negative, and all the way up to the 100th one. And so in this, there's 100 individuals. Well, I don't want to write those out or type all of those out. So a quick little side note, right? 2 times 2 times 2 times 2 can be written as 2 to the 4th power. Well, here, we know we have 100 of those. So 1 minus 0.95 multiplied 100 times can be written as 100 power there. And then when we take, and now we can just type that into a calculator, you get the probability of at least 1 positive is going to be equal to 1 minus 0.0059. That's from that amount there. Or if you just type the 1 minus that in, you get 0.9941 or 99.4%. So the probability of getting at least 1 positive result is going to happen 99.4% of the time out of 100. All right, so that ends the 5.6. So when I'm here on Friday, I'll be able to answer any questions you may have on this. We'll have some time to do the practice bookwork as well and answering any of those questions as we continue wrapping up our chapter 5, halfway through the second half of this chapter. All right, and then for those of you that are still hanging in there and actually made it to the end of this and listening to me and just not writing stuff down, little leftover St. Patty's Day humor for you. So if you were lucky enough to find a 4-leaf clover, one of the things that people try to do with plants and flowers like that is they'll try to save them and they'll press them in between books, maybe even iron to get them really flat. But you don't want to do that with a 4-leaf clover because you never want to press your luck. Speaking of 4-leaf clovers, with spring coming along as well, if you're someone who hikes, I enjoy hiking, and so I got to look out for that.